So it's kind of interesting. We've taken this journey from the interior of the solar system to this point, and if you take anything from this class, I think that the real question we've been circling around is twofold, but it centers on really science as a process more than astronomy in some sense, because we're trying to understand how it is that we go about updating our understanding of the natural world. And that's really the most important question, since most of you aren't going to become scientists. The real question is how you appraise science and look at it from the outside. And so what we're really doing here, and what we are forced to do at this point, is to take on the role of naturalists, right? You guys ever been on a naturalist hike or something like that? Right? So naturalism is a really interesting pursuit, and it's got me thinking about Darwin quite a bit, because Darwin was essentially a naturalist as well, and when he came up with his revolutionary theory, he was essentially hired as a naturalist on this ship that was surveying the coast of South America. And, as we get further away from our own planet, as you can probably tell, we have less and less and less information. And it's getting to the point where our data is pretty thin. So where we have to go from here is we're going to start exploring the moons, and that's mainly what we're going to do this week. And we'll talk about asteroids and comets as we wrap up this course. And hopefully on the last day, we'll try to make some grand statements about the solar system and its history and its future. But there's very little definitely that we can say. I can't sit here and list a bunch of facts or confirmed theories about these things, mainly because they've taken place over eons. And so our job is not so different from Darwin's job at this point, which is something like inventorying all of the different shapes and colors and features of these bodies as we move further away, because really most of the information that we have, especially about these distant bodies and the moons of these distant bodies, is very superficial. We're very much looking at their surface features and trying to infer things about them. And if we're not careful, that can get a little tedious, because the fact of the matter is a lot of these moons share a lot in common. There's some differences, but the explanations are very thin, and they're increasingly thin. So when I was talking to you about the Earth, we have some fairly developed theoretical framework for understanding the Earth, right? We have some base. We can at least measure. We can measure the rocks as they flow out from the volcanoes. We have this sense of how earthquakes reshape the landscape. There's tectonic processes at play, whatever they may be. But we don't have any of this information for these very distant bodies. We're lucky if we've done a flyby with some very brief flyby on the way to maybe look at one of these gas giants or something. So in an effort to avoid the tedium of just running down the facts of all these moons, and by the way, there's hundreds of moons that we could look at, I'm going to try to really refocus us on examining really comparing the similarities and differences between these bodies, because I want to really start thinking about them on a continuum, because many of these moons appear to have they appear to have different origin stories than others. Some of them make sense, and there's a case that can be made that they formed exactly where they're at. But some of them are orbiting as we've seen, particularly with Saturn, some of them are orbiting in strange paths. They're going the wrong direction. They seem to be latecomers to the game. And last week we talked a bit about gas giants and the blurry boundary between them and brown dwarfs and stars ultimately. And so I want us to think about the moons on some sort of continuum as too, and at least open our minds to that we're looking at a different kind of planet in a sense. In some sense, one that's maybe been kicked around a lot in the solar system, which is a bit unconventional, but I think that the research is tending towards a much more evolutionary perspective on the origin and formation of the bodies in the sky. And it's really exciting, but again, there's very little definite theory that we can put on the table about that. These are more trends in the research and ways that people are thinking about it. But you guys are very much in a similar position. Well, of course, you haven't spent as much time at it, but Darwin was also very much uninitiated. So let's think about Darwin for a second. This guy was essentially he came from a family of doctors. He was expected to become a physician himself, and he was shipped off to medical school, and he really found it a drag and wasn't interested. So his dad sent him off to actually a theological school. Now, what's really interesting is that naturalism at the time was in the domain of the church. It was actually a theological pursuit because it was seen as sort of, how would you say, appreciating the diversity and beauty of God's creations, something like that. And he loved this. He loved the taxonomy. He started a beetle collection. He really enjoyed the hands-on aspect of collecting and comparing. And he didn't have any theoretical aims or ambitions at the time. He just sort of enjoyed it. So this guy was not a medical person. He wasn't a scientist. He had no formal scientific training. He actually graduated from the theological school with pretty high in his class. And he didn't really know what to do, but he wanted to keep studying. He wanted to keep inventorying nature. It was just sort of something that he found interesting, which is what we're going to do for the back half of this class, by the way. We're just going to be collecting these little species, if you will, and we're going to compare them and see how they slot together. So anyways, he went on this journey, and he collected notes, and he became interested in the scientific theories of the day. Let's say he read the popular press, if there was such a thing, and he was intrigued, but he was also sort of disturbed by the theories that he was being fed. He didn't find them to fit together in a congruent fashion. So the basic idea of the day was that, yes, species, different organisms, let's say different forms of biology, they would originate in a place, but they would essentially originate in their form as they were, and that was it. And, as he began to see the congruence between different forms of animals, he saw a continuum in that form, right? And this is something that I think is very hard to deny when we look at these planets and we look at the moons. We start to see a continuum. Some of these moons look a whole lot like Mercury, for instance, right? Some of these planets look a whole lot like brown dwarfs. There's a continuum aspect that's beginning to emerge, and as we see actual motions in these exoplanetary systems, we can start to think about, and we see how the stars can change the atmospheres, and we see how the planets actually do metamorphosize over time. We have to start thinking about these things. So anyways, Darwin collected his notes, and he still had no real ambitions, right? He was just kind of kicking these ideas around well after he got back from his journey, which, by the way, took like 5 years, something like that. And I don't think that he was ever really planning on trying to throw this into the scientific mainstream, but he essentially got word that someone else had come up with the same idea, and he actually befriended this gentleman named Wallace, and he basically propositioned him to publish a joint paper, because, well, he had something to offer too, and they did that. And Darwin gets most of the credit, but it was really the two of these gentlemen who both had this idea independently. Now, the interesting thing about Darwin in this case is that, like you guys, he was just somebody who was looking at the facts on the table from a very observational standpoint. He didn't have any training, or he didn't have any appreciation from the inside or any stake in the game with respect to the existing theories of the day. So this is a very, very profound paradigm in that the way that this is perhaps heralded, Darwin's theory of natural selection is perhaps, I was checking out the Wikipedia on this, I think that it's something like considered the most important scientific revolution ever, something like that. And this guy wasn't a scientist. That's the truth of the matter. He wasn't steeped in the theory. He had no mathematical training. He wasn't particularly part of the in crew. He wasn't an academic. And so he was just a guy who looked at the landscape and saw a better way to fit the pieces together that made a bit more sense. And that's where we're at. That's where the world is at. And so, we've been, if we follow the scientific tradition, we're following this very similar, very, very similar situation where we have a story about how, your textbook story about how the planets formed is very much a very old theory that was developed by Kant and Laplace in the 1700s, right? Where these planets form in place. And they more or less form there, and where they form, their environment gives them their attributes, which is so similar to the way that species creation was looked at prior to Darwin. But there's serious problems with that idea. And so the question becomes, what is a better way of looking at these? And so while I can't sit here and tell you what exactly the better way of looking at that is, I can really invite you to consider the similarities and differences on a continuum spectrum yourself and imagine how these different bodies could evolve over time. Of course, Darwin, just like us, was saddled with a somewhat impossible time frame for these processes. Now, in his day, there was still remained a very, very popular mentality that the Earth itself was only a few thousand years old. And of course, that doesn't give you enough time for any of these evolutionary processes that he was imagining to occur. But he didn't much care about that, because one of the things he saw when he first got to the South America and the coast there was he found these bands of this white chalky bands in the mountains that were quite high up that contained fossils of sea creatures. And he also experienced an earthquake while he was there and saw that some mussel beds near the shore had been lifted up such that the shells were now above the ocean. But he thought, this must have taken millions of years for these creatures to have been lifted up into the mountains, if this is the process that does it. So he didn't much care about the popular time frame that people were asserting at the time, which, by the way, was very cosmologically constrained at the time. Right? Why did people think that the Earth was 6,000 years old? Well, in some sense, that was based on a very old cosmological tradition tracing back to the Bible. And of course, the church was still very much part of the state at that point in time. And so that was a kind of impossible thing to argue. It was beginning to be shaken up in Darwin's day, but it was still a very heretical perspective to try to imagine such extreme time spans. But Darwin wasn't part of that club, so he was able to think outside of that a little bit. And you guys aren't part of that club either. I don't think any of you will become professional scientists. Maybe I'm wrong about that. But I think that you're afforded the ability to think outside of the box a little bit because of that, which is really exciting. Which is, in some sense, why I think everybody should take this class or something like it. Because it's very important that normal people who aren't going to become scientists understand that making sense of the world doesn't usually happen in these cloistered halls by specialists, right? These huge leaps in understanding come from people who aren't really poisoned by the existing dogma within some infrastructure, within some institution. And so, anyways, I think we're in a really good position to make better sense of these things than perhaps the professional astronomers could ever be, because we're able to look at it from the outside a little bit. So that doesn't mean that we'll be right, but it means that we at least have a chance, which is cool. All right. So let's review a tiny bit about what we did last week before we cruise on with the moons. Hopefully. All right. So would one of my vocal friends here remind me a little bit about the gas giants and kind of give me a compare and contrast of them? I'm looking to you guys. The only ones who ever talk here. By the way, I really think people should get comfortable with asking dumb questions. And I don't mean dumb questions because you didn't read the textbook or something, but or listen. You were on the phone or something when I was talking, but dumb because you don't understand. Because the truth is, if you don't understand, probably everybody else doesn't either. So you're doing everybody a service. So please, somebody remind us a little bit about what we talked about last. Well, it's been, I guess, a little bit more than a week now since we had that break. But can you kind of give me a sense of the giant planets and how they differ from one another? Yeah, Shane.
Well, the major difference between Jupiter and Saturn and Uranus is Jupiter and Saturn are considered the gas giants of like. They're not made of what we would call ice, like the ice consistency of Neptune and Uranus. They are all bigger than Jupiter.
What's that?
They're both bigger.
They're bigger, yeah. They're bigger. They have simpler molecules, right?
Yeah.
So with these ones we call ice giants, they certainly are icy, but that has more to do with the fact that they have these more complex molecules, right? So Jupiters and Saturns are very similar to stars in composition. They're mostly these simple, small atoms, hydrogen, helium. And their structure really has to do with the different phases of those materials more than different compounds. Whereas the icy ones, Uranus, Neptune, they seem to have a lot of diversity of chemicals inside of them. They have water, methane, ammonia. They even have these rocky cores with metals that look very much like the rocky planets themselves. What do you remember? Yeah.
I got from them like almost like the Saturn and Jupiter's little suns in our solar system because they don't have any real base in them, but they're hot as all get out and even putting off heat. And then the furthest ones, I just gathered from them being far away how they're cold, but they are more like a rock, not necessarily rocky.
They do have rocks, yeah.
They're just so far away. Their orbit's so slow, and their seasons are so different from the distance they are. And I really, really like I've been following Jupiter in the sky, and it does move slow.
Very slow.
So slow. The moon just cruises.
Yeah, I think it's one zodiac, 1/12 every year or something like that.
Amazing.
It's always there.
Yeah, he's right.
Have you? Has anybody gotten a chance to scope Jupiter with binoculars?
I tried.
Oh man, you need a tripod. You need a tripod so it doesn't wiggle.
Yeah.
But if you ever get a chance, do it. If you have a pair of nice binoculars, Jupiter's always in the sky. Well, not always. At some point, it's going to duck behind the sun. But for now, you can go and see it, and just viewing those moons really sets up with your own eyes. It's something that you can't get from looking at a picture. And today, mostly what we're going to talk about is Jupiter's moons. But what you said about them being kind of like mini suns is interesting because Galileo actually thought the same thing. You know, he called them miniature solar systems, right? Because they had these little planets going around them. And this was, of course, this basically sealed the deal on the Copernican revolution, right? In addition to the phases of Venus, the fact that other planets had things going around them, it was like, well, so do we then probably too. And so does the sun. So
Well, the idea that they're not orbiting the sun perfectly, how they kind of have their own reference point too.
yeah, well, they're huge. They're huge.
Yeah, it struck me kind of like, wow.
Yeah. I mean, really, the only thing that keeps them from being suns is they don't have enough of that hydrogen and helium, as far as I can tell. And what's really interesting, we don't have any brown dwarfs in our system, but if we did, they would be very close to being suns, you know? Like I said, there's that fun thought experiment where, hey, at some point, a brown dwarf is so massive that it's one atom away from being a sun, right? And at some point, a sun is so small that it's one atom away from being a brown dwarf. It really just depends on whether it can fuse that raw hydrogen or not. That's the only difference. That's the only difference. Yeah, please.
So if we got a brown dwarf on the outside of our solar system, would we not have night?
Well, brown dwarfs, they're not fusing hydrogen, so they're not going to glow in that beautiful way. And actually, I mean, to be fair, most stars in the sky are much more dim than our star. The overwhelming majority, right? So our star is it's large, it's dense in terms, it's doing a lot of fusion, it's very hot, and we'll talk about what changes the difference in that, but it's essentially like a black body. So I've talked about black bodies before, they're a really interesting thing, but you can think about it as when you heat up something like an iron, you stick an iron in the fire, right? It starts glowing, right? That's basically what stars are. And so if it's not that hot, it's not going to glow that bright.
Still hot.
It's
black, but it's not.
exactly. It could be really hot. It might burn you still, right? You probably had a skillet on the stovetop, right, and grabbed it. I mean, who hasn't done that? And it wasn't glowing red hot, and thank God it wasn't, right, because that would be probably the end of your hand. So, yeah, a lot of these stars are really hot, but they're not that hot. And there's some really magnificent literature about this, that's been coming out lately. I saw a headline the other day, like, star that is, what was it? It was like planet that's surface is hotter than our sun, something like that, which is just like very perplexing at some point because, what is it? Well, it's basically a brown dwarf that's extremely hot. It would turn out to be hot because it's near a star, not because it's necessarily heating by itself, right? So it's getting cooked really hot. But that line is extremely blurry, and so the only delineation that we can firmly make is that it fuses or it doesn't. Now, this is really interesting, by the way, in the terms of species, because you might think, well, what's a species? Does anybody know? Anybody remember from high school, like what's the definition of a species? Nobody? I mean, it's very funny, actually, that there isn't one. That's the answer to the question. That's the funny thing is that, what I learned in high school anyways was that the difference between a species was that they could produce fertile offspring together. So you can mate like a horse with a donkey and get a mule, right? But it can't produce more mules, right? They're sterile. And so, okay, that's a very simple explanation. But it doesn't turn out to work that way in nature. It's not that simple. Actually, species hybridize all the time. And if you even look at the popular theories for the origins of humanity, you see that Neanderthals are supposed to be a different species, but they're breeding with humans, right? So clearly they're not a different species by that definition. So these concepts that we use to chop things up, they can get in the way a little bit, is the problem. They're very useful because you think, okay, we have brown dwarfs, we have planets, we have moons. It's nice because they do sort of fit into these categories, but they're not the hard boundaries that we would love them to be, right? And so I think that I just think there's so much to be learned here from the biological revolution with evolution. And we could retitle this course something like that. Maybe we will next year. I'm actually rebuilding this course for the new Gen Ed requirement right now, and it's kind of interesting. I'm sort of playing with how to do that. So, yeah, so what else did you say? Oh, you said they're very cold. So the Neptunes and Uranuses are far out, and they're cold. That's true. So that was originally feeding deeply into the hypothesis that everything formed in place, right? Oh, okay, makes sense. The gas giants that are far away, they've gotten cold, and that makes sense. The problem is that they couldn't have formed out there because their velocity at formation would have basically flung them out of the solar system. So they must have formed closer and then moved outward. That's sort of the traditional idea, which is, it's a step in the right direction.
Would they slingshot like we did?
That's the idea, yeah, that we would have lost them. But, this story gets even more complex, and I tried to bring this in, and I don't know if I did a good job with it last time, but I was talking about this radius value and the discovery of super-Earths, which we don't have any, and the discovery of mini-Neptunes, which we don't have any, and how there's this really interesting gap between the mini-Neptunes and the super-Earths, although in some sense they're compositionally similar, right? There's just a loss of a lot of the material that you would expect from the Neptunes. And so what people have found is actually Neptunes can be found close to stars in other solar systems. And when they are close to stars, they're losing a lot of that stuff on the outside, right? They are in some sense evolving towards something like a super-Earth, right? Which we could then imagine evolving further into something like our planet. So, and this is really interesting because there was a very old debate in Darwin's day about the formation of rocks on Earth. And there was this argument between volcanism, which was called Plutonism, and Neptunism, which was the idea that they condensed out of the early atmosphere, that the rocks were essentially chemical reactions. And it was essentially abandoned, but in some sense it's been reincorporated because we do think of certain types of rocks as having actually condensed out of the early ocean chemistry and so forth at this point. And so it's not a completely ridiculous idea in some sense that some of our geology could have formed through these chemical processes as our atmosphere and our oceans evolved, right? So, yeah. So there is some reason to believe that these Neptunes wander and that they change, and that in some sense they change towards things that look a lot like the thing that we're sitting on right now. And this hasn't really made it into our popular conception of the planetary formation, but it's certainly being hinted at in the literature, and that's what I was trying to show you with this paper that we went through with the radius valley last time. Of course, we talked a bit about these, what do they call them, the hot Jupiters that are getting their atmospheres cooked off. There's hot Neptunes, like I said, undergoing the same process. These are brand new ideas, though, guys. These are within the last 5-10 years that these reports are even being made. And usually the people who are making the reports are data crunchers who are looking at all of this satellite image data. They're not necessarily the theoretical people, right? They're not the people who are capable of sitting back and looking at the whole discipline as a whole, right? Well, in order to be somebody who's sitting in an office crunching NASA data, your training is probably very specific to that process, right? It's not necessarily like you were trained as a naturalist. You were probably a computational science type of person who's very good at organizing numerical information. And so these reports get thrown out there. Maybe some of them make popular headlines, but that person to come along and stitch it all together into a new worldview is still waiting to be born, as far as I can tell. Yes?
I think it's neat to see these huge gas giants and the Neptunes, and even thinking about them as old as they would have to be to losing a star and coming on another one and completely, because when you heat things up and cool them off, they change.
Oh, yeah.
And so for it to even, the luck of the draw to gain another star, which, I mean, some of them would have to.
To change solar
And
systems.
it would drastically change it. And when you play with magnets, you can get them to hold it. But if you move a little bit, it really fires.
And gravity is exactly the same.
So,
Gravity has the same force laws as magnets, actually.
you see it getting shot into a new star and really change it.
I think that's a really brilliant way that you just mentioned of thinking about gravity. If you take two magnets, right, you have a really strong force when they're close together. You move them away a little bit, and it's like nothing, right? That's exact. Gravity also and magnetism fall off with this inverse square law. It's very, very similar. There's some arguments about magnetism being an inverse cube, but the same idea applies. It's very strong up close, and it's almost nothing after some distance, right? So yeah, exactly. And this idea that planets might change solar system has been so preposterous it's totally unacceptable to mainstream astronomy until right now, right? Until just this very moment when some people have had the luxury of being able to actually run the simulations and say, hey, it's very rare that would even be possible, but it's not impossible. A passing by star can destabilize orbital systems. Again, the huge question, the huge block in the middle of the highway, just like it was for Darwin, is how long it would take. How long does it take to stabilize an orbital system, right? A lot of our planets are at crooked angles. Some of them are perfectly aligned, though. That points to them having different histories, right? If everybody had been here since the exact same moment, we would expect everybody to be on the exact same plane with perfect Newtonian velocities, with perfect angular orientation. Their rotations should be essentially symmetrical with one another. But that's not what we see. But what we do see is some really interesting things, like who has the most perfectly aligned angle in the whole solar system? It's Mercury. And Mercury looks like this old, beat-around rock, right? I mean, I'm just speaking from a naturalist perspective. That thing looks ancient, right? Just like our moon. And so, yeah, there's a real shakeup in the story that we've been telling here. And in some sense, the question is, how long do those things take to happen? And can we afford ourselves that length of time is the other question. Because right now, I'm going to run through some of these moon formation models. And they're accretion models, right? They are all based on the idea that you have this thick dust and gas, and that it sort of clumps together under its own weight, and eventually you get something like a moon that forms out of it. And these are on their face robust simulations, and I'm going to show you one of them that one of my friends down at Caltech did in a little bit here, if we make it to it, if I can stop ranting. But the idea is not completely ridiculous on its face. The problem with it is that it's impossible for you to get pebbles to cluster together into boulders. That seems to be an insurmountable problem, but it's not really, it's sort of one of those things like the wave-particle duality where people are just like, we don't know, but let's move on, right? So all of the simulation models that we have that we're going to talk about for moon formation under the standard model, they sort of just leave that problem on the table. It's a really ugly thing. We're not going to really look at it, and that's that. So I think the evolutionary model might solve that problem, right? Because you can easily crush down rocks inside of something like a Neptune. That's a huge, let's say, pressure cooker, something like that. You have no problem squishing pebbles together and making them molten and crunching them into something that looks like a big, dense piece of rock, which is really intriguing. So, okay. I've got a dead pencil here today, folks. Sorry. Come on. Oh, all right. All right, so, what we know the most of is, of course, the moons that are closest to us. Our own moon, for instance. But the majority of our information after our own moon is going to come down to the moons of Jupiter. Particularly the Galilean moons, which we're going to spend probably the rest of the class today on, because they're the ones that we have the biggest plans for investigating in the future. They're the ones that we have the most information of as of right now. We've been to Jupiter a number of times. Well, not to it. There's nowhere to really land your spaceship. But we've flown around it. We've gotten some really close views of these moons. And they're really diverse and extraordinary. All of the moons of Jupiter are very different from one another. But they are similar to all the other moons that we're going to find in the solar system. So if we can understand the different phenotypes, right, the different, sort of like in biology, you might have like mammals and fish, and I don't know what all the different families are or whatever. But we're going to see those different families of moons in Jupiter, and it'll give us a sense. So when we move on to Saturn and Uranus and Neptune, we'll have basically covered the floor plan for what these moons should be expected. And the cool thing about the Jupiter moons is we can get to them, right? They're far away. It takes a number of years to get out there, but it's not this insurmountable barrier. When we start getting out further and further, we're doubling that length of time of travel to get out to these icy guys, right? So they might have interesting moons too. In fact, some of the, we'll talk about them, but there's some very intriguing moons out in the colder planets out to Saturn and past Saturn. There's really interesting moons, but they're so far away that it's unlikely that we're going to get to them first. And so these moons are really interesting, and the presence of liquid water on some of them is also really intriguing because there's a great hope, of course, that we'll find something like life, right, or something like proto-life. So we'll see. We'll get to that. All right. This is what you'll see if you ever do manage to get binoculars on a tripod. You can see this. I saw this myself maybe a month ago. It's a very, very profound experience to watch these things. Now, this was first seen by Galileo back in 1610 with his 20x power telescope, right? And I think that this was this is a very different kind of revolution too, by the way, than the one that Darwin partook in, right? So there's kind of like two different types of revolutions you can have in science. One is where you observe something nobody's seen before, and one is where you take everything everybody's seen for ages and you rethink how it all fits together. These are very different processes, and of course Galileo was certainly more of the seeing something nobody had seen before type of thing. And he actually took Copernicus had published his idea before Galileo's time, and Galileo, upon seeing these things, was essentially convinced that this guy everybody thought was crazy was absolutely right, that these bodies were orbiting one another, and that was essentially what was happening with the whole solar system. So that's a really interesting kind of revolution too. But of course, we have less access to that since we're not sitting here with telescopes. Maybe that will change in the future. We'll have a more hands-on part of this course. It's very difficult to do astronomy in college, though, because we'll be up all night, and that's probably not good for your other courses. All right. So there's these 4 moons. I think that Jupiter has somewhere in the neighborhood of 80 moons, but we're going to talk about these 4. Now, what's really interesting about these 4 is that they appear to be quite stable for the most part, and they're in these beautiful resonances with one another. And just to remind you guys why resonance, I want you to grok this concept when you leave this class, like what resonance really is and why this works out and why it stabilizes orbits too. So if you think about it, if you've ever, I don't know if any of you guys have kids, probably not. Maybe you have like some little nephews or little, even, little siblings. You like push them on those swings, right, in the park? And you notice that if you push them at the wrong time, right, as the swing's coming towards you, it's a disaster, right? It could even knock you over, right? And if you push them too late, it doesn't do anything, right? But if you push them at just the right moment, you can get a huge kick into that swing, right? And you guys probably remember this when you were kids, like playing on the playground. You try to get, you want to get your friends to get you to basically flip over the top of the thing, right? And they do that by putting that impetus, that push, at the exact right moment. And that's what's happening with these moons. That's why they're so stable, is that each time one comes around, they'll line up in this perfect way so the next one gives it that kick at the exact perfect moment. And you can get chains of these resonances, right? Where that push is coming at exactly the right moment. And when the chains are in perfect harmony with one another, and I use the word harmony because these are the same resonances that we hear when we hear pleasing music, right? These overtones, we would call them intervals in music, but they're essentially chords that are melodious in music. They're the same resonances that keep the planets in orbit. And of course, the very ancient natural philosophers were obsessed with this. They saw music in all of these orbits and the timing of the planets as they pass through the sky. And they're right about it. And it comes down to gravitational harmonics as opposed to acoustic harmonics, right? The same thing's happening with music too. When these waves of sound compression, let's say waves on a string, are in harmony with one another, that kick is happening so that it constructively interferes and builds up a bigger tone that's more pleasant to you, right? That's why you get these beautiful tones when you have harmony, when you have these overlapping, essentially the oscillation is coming in at the same moment for these notes. Okay, so it's the same process, and we see these musical notes appearing, which is pretty cool. All right, next.
Are they lining up in the same lines that your chords you would hold your chords? Is that what they're implying?
Yeah, it's like, it takes a tiny bit of music theory to grasp this, but when certain, a string, when one string vibrates, say, 3 times, and another one vibrates 2, those notes, they will overlap periodically. Those vibrations will overlap. And the vibration between, say, one at 3 and one at 2 is called a perfect fifth in music. Okay. And the perfect fifth, if you just use that 3 to 2 resonance, you can build the entire keyboard out of it. You just keep going up by a fifth, and eventually you'll get back to your starting point, and you will have built the entire piano as a result of it. So the perfect fifth, that resonance of 3 to 2, is essential to our Western concept of music, essentially. And so there's 3 to 2s that we see in nature. There's other intervals as well, which are perhaps less harmonically pleasing, but we use them. A lot of music that you guys probably enjoy, which has its roots in jazz and blues and basically Islamic territory and Arabian music, it has a lot of intervals that are not perfect, right? They're not these perfect fifths. They have these minor overtones and so forth, which are different vibrational resonances than these basic ones. And so the resonances in Jupiter are actually tending towards the more perfect intervals, but they're not. Some of them are not quite there yet. It's not perfected yet, and so that again gives you this idea that these resonances are stabilizing the orbits across time. That as things find these perfect kicks, right, as they're getting that push on the swing at a more and more appropriate region, that pendulum is just becoming very stable. It's very reliable is another way to think about it. Because, there's of course this selection concept going on in terms of us making sense of these systems. Why are there only 4 moons there? Well, maybe they're the only ones that had the resonance with one another. They were at the appropriate intervals with the appropriate, right? Because your speed and your distance are related, right? How much pull of gravity you get comes down to how close you are to a given planet. So maybe there were lots of moons there. Maybe many have come and gone, but they were not selected to remain, much the same way that some species might not be adequately prepared for their niche, for their environmental constraints, and they didn't survive, right? So maybe they, God knows what happened to them. Maybe they were cast into the Oort cloud. Maybe they're part of another solar system for all we know. Maybe they were they crushed into each other and became the debris of the asteroid belt, right? We don't know. So one thing that's really interesting, and this kind of makes sense, is that the density of these moons as we move from the interior to the outside scales appropriately. So the interior moons are more dense, which makes a lot of sense in terms of the fact that, of course, they're going to be moving faster on the interior and they're heavier. And it gives us a little bit of an idea of, well, their composition, which we can infer, which is going to teach us about possibly what's going on inside of them, below the crust that we can see. Some of them have magnetic activity, and we have to piece that together with the density. So, this is generally taken, this density model is generally taken, well, okay, the heaviest stuff was closest. They, of course, formed in place, right? This uniformitarian perspective that we've tried to apply to the solar system, which is on the move. These moons formed in place well. The most material was closest to Jupiter at the time, and so of course all the dense stuff was there, and that's why the denser ones formed. But I think an argument could also be made that anything that's dense that joins the system is going to find its way closer to the system, is closer to the central mass, Jupiter, and also organize itself accordingly. So that's a little bit of a difficult chicken from the egg problem to separate. All right. Let's take a look at these. All right, so here we have them. This is in the order in which they appear. So we have Io, we have Europa, Ganymede, and Callisto. And they all have radically different surfaces, which is quite fascinating. And hopefully we can say something interesting about each one of these surfaces. Ganymede has both Ganymede and Europa have these folds and cracks in them, which seem to indicate some sort of almost tectonic-like processes happening, like the crust has been shifting and bending and flexing. Io has got this incredibly sulfurous surface. It's very volcanically active. It has mountains, too, which don't appear to have anything to do with the volcanism at all, right? So the mountains on Mars, for instance, are almost exclusively due to the volcanoes there. But these mountains, despite all of the volcanoes on Io, don't seem to have been built by volcanic processes, which is very intriguing. At any rate, let's look at each one of these in detail as opposed to trying to go them. I just wanted you to see them all together in one place. All right, so like I've kind of hinted at, the general mechanism that you're going to find in your textbook for the formation of these moons is basically identical to planets forming around a star in the standard model, which has to do with this gaseous protoplanetary disk. There's something like that around these Jupiters that is part of the theory. And essentially the differentiation comes down to the accumulation of different densities of materials at different distances from the planet, and you get everything. So I thought that I would, I'll show you a little video here about this too, because like I said, somebody else can show you in a computer simulation better than I can probably explain it to you. So it's interesting, even over the last 10, 20 years or so, people had to, of course, revise these models a little bit. There was this, started off, right, the very basic idea, which was not that long ago, 2009, was that all of these moons formed exactly where they are right now. This was followed by a paper that involved a very similar process to the one you mentioned with these, well, the one that we deduced with the Neptunes forming and moving closer and moving away. There was this thing they called essentially the grand tack hypothesis, which is like a sailing term, I guess, that these moons essentially moved from one place to another to give them their different characteristics. And then recently, this has been kind of, both of these have been sort of squashed together into something that involves them forming in place and moving together, or moving into their new places, which, like I said, was developed by Batigan down at Caltech. And the idea there is just that there's these, inside of this gaseous disk and this dusty disk, there's just little pockets of let's say, almost vacuum, right? Little pressure bubbles, let's say. And those tend to nucleate, those can collect things like these pebbles, right? And somehow they accrete, nobody's really worrying about how they accrete, but they do, and we get the moon formation, which is what's being detailed here. But let's watch a little video about it, because I think that will be worth, in some sense, 1,000 words. Let's see if I can get it to play anyways.
Based missions. The orbital machinery of these moons has been understood for centuries. The exact story of how these satellites formed, on the other hand, remains a remarkable mystery. A new theory, drawing upon analytical calculation and large-scale computer simulations, is helping shed light on their origins. Jupiter was born within a protoplanetary disk that orbited the Sun during the first few million years of its lifetime. And as gas and dust rained down upon the newly born planet, Jupiter became encircled by its own circumplanetary disk of satellite building material. In time, this disk grew more and more dusty thanks to a balance between headwind and updraft attained by icy dust grains, only about a millimeter in size. Eventually, the ring of dust around Jupiter became so massive that it collapsed under its own weight into thousands of satellitetesimals, icy asteroid-like objects, about 100 kilometers across. The orbits of these satellitetesimals are shown here as orange ellipses. Over thousands of years, satellitetesimals coalesce into moons. The mass of the growing satellites is depicted here with a logarithmic bar chart on the right. As the mass of a moon crosses a threshold, it begins to raise spiral wakes in the gaseous nebula and migrates towards Jupiter, leaving behind a mess of satellitetesimals to birth the next moon. Here we see the first two moons, Io and Europa, form in about 6,000 years. As sequential satellite formation unfolds, the orbits of satellitetesimals grow more and more excited. Eccentric orbits slow down accretion, and it takes longer and longer for additional moons to form. In fact, Ganymede makes its debut almost 30,000 years into the simulation. Close to Jupiter, the converging orbits of the first three moons stabilize, establishing the orbital clockwork of the Laplace resonance, wherein for every 4 orbits that Io completes around Jupiter, Europa completes 2 and Ganymede goes around once, with the system returning to its initial state every 172 hours. Our calculations show that this celebrated orbital architecture must have been built from the inside out over a timescale no shorter than about 10,000 years. Eventually, radiation from the newborn sun evaporates the gas from the Circumjovian Nebula, leaving behind a disk of icy debris and triggering the formation of Callisto. Because of the gas-free conditions in which Callisto forms, its conglomeration takes much longer than that of the other moons, nearly 9 million years. In particular, it achieves about half of its mass in the first 50,000 years, but then takes more than 8 million years to grow the rest of the way. Jupiter's moons are mysterious and fascinating places that contain water, salts, and maybe even the building blocks of life itself. Understanding the formation of Jupiter's moons helps us illuminate the intricate physical processes at play in the solar system's early evolution and unlock some of the deepest secrets held by the planets.
All right, so Batigan's trying to argue essentially that there's these dust traps that are set up It's very cold, and this allows for the accumulation of these bodies. And you might be right about that. One thing you might have noticed, though, that's really interesting is these timescales are unbelievably short. So we're talking about these moons forming on the order of 10,000 years. That's an incredibly short timescale. I don't know. I wrestle with that. So anyways, if you want to hear more of this guy, we did a podcast with him. I guess this is number 96. And he's a really interesting character. He's got a rock band, too, that's pretty popular down in LA. He's a cool guy. And he's done a few other podcasts that are really interesting. I think he's done Lex Friedman's podcast, too. Okay, so let's look at Io. Io kind of looks like a big piece of moldy cheese or something. This is the innermost, right? It's the third largest of all these Galilean moons that we're checking out. Named after the mythological character Io, from the Greek tradition, a priestess of Hera who became one of Zeus's lovers. I don't know too much more about that story, but it bears repeating that we have reverence for these mythologies that persist into our modern nomenclature. By the way, Galileo wanted to name them after his sponsors, which is pretty hilarious, right? Can you imagine if we named things that we found in the solar system after, Nationwide and Pepsi, and I could see it. All right, but that was unacceptable, and the Academy fought back, and they ended up naming them after, in the tradition of the other planets, after the Greek pantheon and Roman pantheon. So it's a little bit larger than our own moon. It's actually the fourth largest moon in the solar system and has the highest density of any moon, which should be something of a red flag in terms of its formation. That's really, really incredible how dense it is. So, and it also has 400 active volcanoes, which is amazing because it appears to have tons of convection going on, right? Despite not having much of a magnetic field, which is very perplexing. I think the magnetic fields are probably the most, aside from the formation that we're continually dancing around, magnetic fields are probably the least understood aspect of this whole puzzle. First time we went and saw Io was Pioneer 10 and 11 probes. That was back in 1973. And they got some estimates of its mass from this. And they were also able to see that it had a very thin atmosphere. And there was a very intense radiation belt that was sort of in the path of Io, which plays a really remarkable story into Jupiter's own magnetic field. It turns out that Io acts as something like an amplifier for Jupiter's magnetic field, which is quite incredible. I'll talk about that more in a second. Here's a close-up. So the Voyager 1 and Voyager 2 came by in 79. They had a much better imaging system. And it looks like Voyager 1 came by within something like 12,000 miles, which seems far away, but it's actually close enough to get some of these really incredible close-up images. And you see this strange kind of multicolored landscape, which didn't have any impact craters. Now, that was really interesting to people because generally, first of all, as we'll see, some of these other moons are incredibly cratered, particularly the furthest out. It's just so cratered that there's craters on top of craters on top of craters. You can't even possibly date the thing because there's so many craters. And of course, the way we used to date these bodies was by impact craters, assuming, some steady stream of impacts. This is how people tried to date the moon. And if you'll recall, the age that you come up with if you date the moon that way is on the order of trillions of years, which is an interesting data point by itself. So this thing had no impact craters on it, which was very strange. And this got people to thinking about why that would be the case. And the conclusion that they came up with was that it's constantly being resurfaced by its volcanism. It's essentially a giant lava field, right? So let's keep going here. In 95, quite a bit later, the Galileo spacecraft came to check out Jupiter, and it started to study this intense radiation belt, which was very perplexing because we have radiation belts set up on Earth in some sense, but they're largely a product of capture of these high energy particles from the sun by our own magnetic field, This one was different, right? It wasn't in that same position that it should have been. And, people started thinking about why the heck that is. And it turns out that these eruptions that are coming off of Io turned out to be visible. They were actually streaming out outside of the atmosphere. It's like if we had a volcano that was so intense that it was actually kicking the plume out into outer space. And we'll see a close-up picture of that in a second. And it turns out that those particular compounds have the proper metallicity to be an ionization state that they can actually be conductive. And so what they do is they essentially set up something like an antenna that's capable of magnifying Jupiter's own magnetic field. And you get this real feedback loop between Jupiter's magnetic field and Io's stream of, volatile, nasty chemicals that are getting spit out from its interior. And this was all, this is really just being put together in the 90s, which is kind of incredible. All right. So in 2000, Cassini went by. It made more detections. This is a picture from that mission. And Cassini was able to see that there was some auroras that were evident. Again, more evidence of this intense radiation belt interchange that was going on. They also saw some actual volcanoes erupting for the first time. So the New Horizons came by. The volcanoes were really seen up close the next time in 2007, so 7 years later. This New Horizons spacecraft, which was actually the one that went out to see Pluto. We got our first beautiful images of Pluto, you may have recalled, when you all were quite young. And so we actually began to get some pictures of these volcanic plumes and put the pieces together as to what was actually happening here. And I think people had not expected that a moon could be so animated and so alive, like for lack of a better word, right? Our experience with moons to this point was essentially our own, and observing these things from a distance. And of course, our moon is completely geologically dead. There's some evidence that there may have been volcanism in the past, right? That's the standard story with these mare, these dark spots, right, as basaltic lava beds, ancient ones. But I think people were really, really shocked to see that a moon could still be so active. And so the question becomes, why is it? How is it that something could have formed on the same timescales as everything else in place, and this one's very, very alive, and nobody else seems to be? Well, the standard explanation is that, and it makes a lot of sense, that the thing is so close to this enormous body. Remember, Jupiter basically accounts for most of the mass in the solar system outside of the sun. Well, as this thing is getting dragged around very close to Jupiter, its interior is also getting dragged around and sloshed around quite a bit. This is kind of similar to the explanation we try to concoct for Mercury's magnetic field. It's also getting sloshed around quite a bit. And so the same idea is thought to account for all of this geologic volcanism and magmatic activity in these plumes and so forth from Io. All right. I'm going to skip that for now. And this is just a schematic for the enhancement of Jupiter's own magnetic field. It's interesting. So just to clarify this a little bit for you. So the magnetosphere of Jupiter kind of organizes all of this electrically conductive gas that's coming off of Io. And what it does is there's something like a ton per second of this material that's flowing out of Io. So it's quite significant accumulation. It's basically ionized sulfur, oxygen, and chlorine, sodium, potassium, a bit of molecular sulfur dioxide, sulfur, sodium chloride. So these are all very salty. And like when you think of salt, you should think of electrically conductive stuff, right? If you, again, if you ever take a chemistry or biology class, you're always going to be mixing up these solutions. By the way, or maybe a better way to think of it is, if you do any athletics or anything like that, they're always telling you to drink these, drink salts, right? And why is that? Because of course, all of your neuromuscular signaling depends on salt gradients, right, in your body. Salts are critical because they have that electrical valence to actually conduct electricity. If you take water with no salts in it, it's basically an insulator. You can't drive a current through deionized water very easily. You have to actually start to break down the water molecules themselves, and that takes a huge current. But when you get salts introduced, then they can actually participate like little wires. And so these are very, very salty compounds, and I think that's what contributes to it for the most part. Let me make sure I said everything I want to about these. Yeah, that's fine. So you basically have this feedback where it builds up, it adds its own swirling electrical fields to it, which reinforce Jupiter's magnetic field. And of course, they're patterned by Jupiter's magnetic field, so it makes sense. It's this feedback loop. Now, oh yeah, really nasty stuff, which is, as we'll see, like, yeah, and it's not a place you want to be as a person, right? So, like I mentioned at the beginning of this class, that we're really looking for places that we can set up a base to, do further research. It would be really nice if we could set up some sort of base there eventually, and then send spacecraft to study all of the moons very easily from that base. But you don't want to set up that base inside of this radiation belt. That's a really, really dangerous place to be. Because, of course, the stronger that this magnetic trap becomes, the more that it's swooping up all of the radioactive particles from Jupiter, from the sun. It makes for a really vicious vortex of really highly, let's say, for lack of a better word, energized material that's going to mess you up, and really high energy radiation that's going to destroy your DNA. So you don't want to be there. And so when we start looking at these outer moons, those are certainly more appealing. And particularly the really far outer ones, which don't seem to have any surface remodeling. They seem, let's say, tectonically stable, right? And that's a much more appealing place for a base in some sense, from a human perspective. All right, so let's look at the interior of this thing. So, like I said, it's extremely dense. It's not quite as dense as the Earth, but it's on the same scale. It's primarily composed of the same stuff as us, though, silicate rock and iron. What's the most important point here, since I want to make it through these other moons? What's really interesting is that despite all of this convection and so forth, and the iron interior and so forth, we don't see a strong magnetic field, which is very, very perplexing, right? Again, I think we're going to have to fundamentally re-examine where these magnetic fields arrive from. Maybe it feeds into our evolutionary model. Maybe these magnetic fields are established in some earlier phase of their evolution, right? Maybe if it is true that something like an Earth evolves from something like a Neptune or something like that, well, those have pretty powerful magnetic fields, and maybe that gets encoded into the materials of the Earth at a very early point, something like that. But it doesn't seem like all of this convection is sufficient to drive the production of a magnetic field, which is a bit perplexing in this guy. Let's keep going. Now, I guess I already mentioned to you that it's being tugged really hard by Jupiter. This is where almost all of its heating is supposed to be coming from. This is very different than the heating that we see, our own geothermal heating, right, which is primarily thought to be driven by leftover formation heat and also radioactive decay. But this thing actually has something like 200 times the heat that it should be able to produce based on radioactive decay alone. That's very, very interesting. So it's kind of unique in that it's very, very close. It's getting tugged, it's getting sloshed around. And that makes it sort of an outstanding creature amongst all of these that we're going to look at. All right. By the way, why is the thing orange and yellow and stuff? This has to do with mainly with its sulfurous composition, right? You guys have I imagine that makes for a very smelly planet too. If you guys are aware of the smell of rotten eggs, that's probably what you would expect. A few more pictures of some of these calderas. There's a very active one there, which is quite astonishing. I mean, they've seen new since they visited. I think that the images here on the left-hand side, this image was taken in 1999. The next one was taken in 2000. So there's new volcanoes appearing all of the time. This is basically a giant, what would you call this on Earth? Like a, I can't remember. But there's a few of these in Africa, particularly in Ethiopia. They're basically just giant open gashes. They're not mountainous volcanoes. They're more like lakes of magma. Really pretty incredible stuff. So it's constantly being remodeled. And then this is all very, very shocking to people because we expect moons to be old and sort of dead, but something about its proximity to Jupiter is keeping it alive, it seems like. This is a picture, let's see, when was this taken? I'm not sure when this was taken. This is one of the more recent ones, though. This might have been the Cassini image. But you can actually see this material getting shot off into space. I mean, these are volcanoes on the scale that we can't even imagine on Earth, right? I think there was this Hunga Tonga eruption very recently, which was huge by modern standards, one of the biggest volcanic eruptions to occur in history. And it was nowhere near launching material out into outer space, okay? So these are just constantly happening. This thing is not a place that you would want to be. All right. Like I mentioned, these are some of the volcanic structures. Again, the thing has quite a bit of, it has tectonic features. A lot of these mountains are not thought to be created by volcanism. And so it has a lot of those same things that we would expect. Tons of convection. It has tectonic features, so the landscape is being crunched and shifted around. And yet we don't see this beautiful magnetic field that we see here on Earth. And why is that? It's not entirely clear. We don't know. All right, there's a picture of its atmosphere. Now, its atmosphere actually has an appreciable amount of oxygen in it, which would otherwise be quite useful, but I think everything else is going to make it too unattractive. I don't think there's much hope of finding anything living there just due to the constant surface remodeling. It's too violent of a place is the thought. But we'll see. Again, we're going to have to set up a base much further out to get anywhere close to landing on this thing. All right, the next one out is called Europa. This is actually the smallest of the four. And, again, these four are a few of the 80 moons of Jupiter. They're just the ones that we can see. They're the first ones Galileo saw. And this makes them, in some sense, most interesting for study. It's also the smoothest surface. It has the smoothest surface in terms of its granularity of any object in the whole solar system, which is quite interesting. And we think that that's probably because it's got a water ice crust on it. It's very slick, like a pond that's frozen. Here we can compare its size to the moon. It's a little bit smaller than the moon, but it's comparable. Although it is the least massive of all these Galilean satellites. It's still being still the least massive of all of these, it's still more massive than all of the other moons in the solar system combined, essentially the smaller moons than it. And again, very similar composition to the terrestrial planets. It's basically made out of the same stuff as us. It has everything that we have here, just in lesser quantities, which is really, really interesting, again, on our naturalist trip through all of these different bodies. All right, I don't have anything to say about that. It has these really interesting cracks, though. This has been puzzling people lately, because the way that these cracks are thought to have formed, these are in the icy surface, is that, you know, as the thing sort of sloshes around, you should get these banding structures. The problem is that the bands aren't exactly lined up with one another. And so what we would think is that if it was getting, if these cracks were forming because due to its rotation, and essentially like if you were just spinning something and it started to fold on itself, well, that would make sense. But if that is the case, and that's the best idea anybody can come up with, well, then the thing appears to have changed its orientation multiple times over the course of its history. Which, how do you do that? What causes it to change its orientation? Is that something that happens on other planets? Is that something, you know, that was very much an interesting idea that was entertained with regard to the glaciation periods on Earth back in the 1950s. There's this really fascinating book written by Charles Hapgood, where he imagines that the ice ages are on, they come on very quickly because the pole of the Earth kind of tilts a little bit, which is not what people think right now. It's actually owing to a number of cycles regarding the precession of the Earth as it moves, as the tilt changes very slowly, as different things happen and accumulate. All of these cycles result in those. But Hapgood's idea was entertained, and it does seem like there's precedent for it, at least in Europa. It does seem like bodies can change. But what's fascinating about them changing is that if they change, it doesn't seem to affect their orbit because it's still in a stable plane with the rest of these. So, I would offer maybe another idea that perhaps it's much, much older than we think. Maybe it's spent a lot of time in different systems. Maybe it's been a moon of other places and it was at a different angle at those points in time. There's an idea. All right. It also has these thin little dark streaks. These are interesting. They call these things lineae, which really just means lines in Latin. The idea with these is that there's potentially these eruptions of warm ice onto the surface, and those expose different surfaces. That the eruptions warm the ice and allow the crust to spread, and it sort of expands and exposes these cracks in it over time. That seems reasonable. Here's a close-up of those things. I mean, it's just a very, very mottled surface that seems to betray a history that's very varied, right? There's layers of these structures. It seems like it's been through a lot of different interactions over the years, which to me points to it having some history which is stepwise as opposed to maybe this idea. Now remember, looking back at this latest simulation from Caltech, this thing is supposed to have essentially formed as it is in a matter of thousands of years, right? And then it just sat there for the next few billion. I think that's a rather tenuous hypothesis looking just at its surface features. All right, so the other thing that's really attractive about it is that based on the density of this thing and based on what we can see just by doing some basic radar studies of the surface and so forth, we get the idea that there's an outer layer of water, a huge layer of water actually, something like 100 kilometers thick layer of water beneath this ice. Now that's a ridiculous amount of water if you think about compared to our own planet, right? I mean, our planet's not even entirely covered in water, first of all, right? Where we have, well, that's probably a good thing because we can sit here and be nice and dry. But this thing is absolutely covered in water. And not only is it covered in water, it's covered in 100 kilometers of water. I think, I don't know the kilometer conversion for the depth of the deepest points on the ocean, but I think it's let's say, on the order of 5-10 kilometers, something like that, right? So we're talking about 10 times that amount of water on this thing, which is really, really incredible. What's that? You can, yeah. I mean, water is an incredible chemical. I don't think that there's any other chemical that rivals it. It has the ability to do everything that keeps us alive. There's a good case to be made that all of our biology is essentially organized by water. And water can form structures even in the liquid form, right? It can articulate with itself. It does all of the work inside of our body, from what I can tell. It folds our proteins properly, probably plays a huge hand in how our DNA is transcribed, just everything. So yeah, that's why people are super interested in Europa. And the hope is that we can basically get down inside of the thing and maybe we'll see something, right? Maybe we can start to answer some of our questions about the origin of life. Why is the origin of life such a crazy thing? Well, is it a thing that happens discretely? Is the origin of life a cell, or is it something before a cell? Are there organizations of matter that have that same characteristic, that striving to exist that Darwin pointed out, that are being selected for by their niches and are competing with one another? Is there something before a cell that's doing that? Well, this might be a great place to look for that. Problem is, we have to get through that ice shell to get down into it, right? And by the way, it's thought to be quite a salty ocean, which again is very useful because all those salts are extremely important for setting up the communication systems inside of our own cellular machinery. All right, so I'm going to zip through some of this. Here we get some pictures. This is from the Hubble Space Telescope, and you can see some of these geysers erupting from the surface. Now, geysers are really interesting. Actually, this plume's extending for 200 kilometers above the surface there, which is something like 20 times the height of Mount Everest. These are huge, huge, right? And they're thought to be essentially, there's a tidal force as it's being yanked around, and it's sort of squeezing out the liquid from the interior, so they're being pressured out from the interior. So the question is, how do we get down into this thing? And, you know, the idea, there's a couple of ideas on the table. One is you drill through it. That's a very difficult proposition because drilling is actually extremely difficult. You need huge blades. The blades break, or the drill bits break. They get cold, they break, exactly. So the idea that people are really playing with is, what if we just take something that essentially has a nuclear furnace in it, and we just set it on the ice and just wait for it to melt, and it essentially digs its way down. And I think that's what people are leaning towards. Let me see if I can tell you about that proposal. Well, oops. By the way, the atmosphere on this planet too is very high in oxygen and traces of water vapor. Again, this might make a really, really interesting place for us to find some hints of life. Doesn't really have any weather, which is also might make it a very easy place to explore. So it looks like, and this is the last thing that I will tell you guys today. This MELT probe was designed back in 2001, right? And the next proposals are going to be flybys. So in 2014, the Congress essentially approved an $80 million funding bill to continue to develop concepts for how to explore this thing. But we're a long ways off from even being able to do more flyby missions. This thing's a few years away. Even if you launch a spaceship, it takes a while to get there. And then the furthest that we've gotten is basically conceptualizing how we would even get down underneath this. So one hope is maybe we could actually just get to one of these mantle plumes and start sampling what's coming out from underneath, and that would give us some sense. I think that there is a very reasonable chance that we might find some prebiotic materials there. Would we find anything like a cell or an organism? I don't know, maybe. But I think what would be even more interesting is finding something that was on its way to becoming a cell. Because right now we're completely at a loss as to how this whole thing got started in the first place. Life is extremely delicate. I don't know if you've ever noticed, but you break really easily. It's very, very difficult for an organism to survive under any conditions, let alone through the initial stages of assembling itself into something strong enough to withstand the pressures of daily existence.